Having me. I got to see this space for the first time, I don't know, about 4 or 5 months ago. And when I came, I was here for a conference, and I came to visit here at BIDS for an hour or two, and literally was taking pictures of the place to take back to Illinois, saying, "This, we need this." So it's really great to be able to give a talk here now, having spent a lot of time telling people at Illinois that this is such a great thing to have. So, like you said, my name is Claire Sullivan, and I am in the Department of Nuclear, Plasma, and Radiological Engineering at the University of Illinois. And today I'm going to talk a little bit about some sensor network stuff that we have going on through a few different sponsors who I just would like to throw a shout out to. A lot of what you're going to see today is sponsored by DARPA through the Young Faculty Award, but we also are funded through the National Nuclear Security Agency through a couple different consortia, predominantly the Consortium for Non-Proliferation Enabling Capability, or CNEC. But we also are with a couple other of the NNSA consortia and have some funding from DITRA, so just have to give my thanks there. And just have to start with the obligatory outline slide of what are we going to talk about today, and more specifically, when are we going to be done talking about it. And so I'm going to talk a little bit about the problem, but here's the preview. Nuclear detect the illicit movement of nuclear material that could be in something like a nuclear weapon or a weapons component. Maybe it's a dirty bomb, some sort of radiological dispersal device. But the idea is that we are detecting ionizing radiation. Now, I know that in this particular environment, we'll have people ranging from nuclear engineers and radiation detection experts to people who don't know anything about radiation detection but are brilliant data scientists, geospatial people mixed in here. We're going to talk about all of it, hopefully at a level that everybody is going to be able to be on the same page, but feel free if there's anything that I'm talking about that is just not something that's making sense, let me know. But, okay, so the problem is that detection problem, and we'll talk some about a data set that we've been using at Illinois and that we've been collecting at Illinois on, we call it UIUCNet. Then, how can we be in a data science talk without talking about some sort of machine learning? So I'm going to talk about several different machine learning concepts, and then I'm going to get totally out of my element here and start talking geospatial. I am not a geospatial person. I have a postdoc through the Cyber GIS Center at NCSA, which is the National Center for Supercomputing Applications on our campus, and he's the one who's done all of these GIS techniques. So, I'm not a GIS person, but I stayed in a Holiday Inn Express last night. And then talk about how we're going to start fusing sensors in a giant sensor network. And then, of course, we have to end with future work because this work is never done. So, the problem and the data. I am going to use a term that was coined by one of my sponsors. And specifically what he likes to call the dumb physicist approach. This is his term, but I think it's kind of funny. And what the dumb physicist approach is let's say I am some sort of first responder. Maybe I'm a police officer or a customs inspector, and maybe I have a radiation detector. Now, around us, all the time, we have natural radiation background. It comes from the soil, it comes from building materials, it comes from people, it comes from all kinds of things. It changes. It changes with position, and it changes with time. But we understand the process to be a Poissonian process, so therefore we can know what its mean is, and we can know what its standard deviation is. And the question is, as I have my detector and I start wandering around, my detector's measuring radiation. In this case, we're going to be talking a lot about gamma ray counts, gamma dose. I can figure out what my mean is. And the dumb physicist approach says, well, we need to set some sort of threshold, some sort of alarming threshold that says, aha, I have found something that shouldn't be here. I've found a higher amount of radiation than I would expect. And the dumb physicist approach uses a K-sigma method, where we could say K is maybe 3. So if my gamma ray count rate exceeds 3 sigma above my mean background rate, then I'm going to call that an alarm. And to my particular sponsor who coined this term, that is the dumb physicist approach. But we in this room understand statistics, know that if I set 3 sigma as some sort of alarm, we expect there to be false alarms. And we know how often those should be for a Poissonian process. And so false alarms in this world are bad. False alarms lead to bad days when all of a sudden you're informing the federal government, oh geez, we think we might have found somebody smuggling a nuclear weapon. You don't want to get that wrong, right? That's going to lead to a pretty big response if you think that's really going on. So minimizing false alarms while maximizing the probability of detection is the name of the game here. And so, of course, I have to start with an XKCD comic where we start talking about p-values, but really it boils down for the nuclear engineers in the room. We have radiation sensors. We could be measuring gamma count rates. We could be measuring gamma ray spectra. These are two different forms of data. They tell us different things that eventually get to the same thing, but we're going to be applying machine learning to a large network of these detectors. And should we be applying it to gamma counts, gamma spectra, both? We can bring in geospatial information. How can we bring in all of these tools to play to maximize that probability of detection while minimizing the probability of false alarms? So I'm going to talk about a bunch of different things today. I'm going to talk about some of our learning methods, and specifically as they apply to background. We'll get into the GIS methods, and then I've got some sensor fusion stuff to talk about. Let's talk a little bit, though, about the data itself. So one of my sponsors, I said, was DARPA. DARPA has a program called SIGMA, and SIGMA's goal is to get a whole bunch of really inexpensive radiation detectors, mobile, time-tagged, geotagged collection out into the field. And when I mean a whole bunch, what I mean is on the order of 1,000 or 10,000 detectors. Okay. With the type of detectors that we're using, this could be somewhere around 2 terabytes of data per day. So just give you an idea of how much data we're talking about. Before I even met the friends at DARPA, I started seeing a lot of other sensor networks coming online. Whoopsie. Now I did it. Okay. So for instance, this here, SafeCast. This is a little Geiger counter. You can buy it as a kit. You can make your own. It's got GPS on board, and this sprung up as a citizen scientist thing after Fukushima. You had, obviously, a pretty bad nuclear event happen in Fukushima, and the citizenry wanted to know, am I at a place where there is elevated radiation? Am I buying food that's contaminated? Is the water that I'm drinking contaminated with radiation? And so they all just started building their own little detectors and uploading their data into, through a nice API. You could go download this data today. Last time I checked, it was over 35 million unique measurements, most of which is around Japan. But now other people have started saying, hey, this is pretty cool. So what happens when every single person on the planet is carrying one of these things? That's some interesting data. As an example of that interesting data, here's the output of SafeCast looking at Washington, D.C. And you see here, we've got the National Mall. Here is my gamma dose. And most of what you see here, just a nice little heat map, is blue, dark blue, meaning low dose. Except I've got this thing right here. Anybody know what that is? No? You've heard this one. You don't get, yeah. You've heard this one too. Okay, here's a hint. That is the Washington Monument right there. Close. World War II Memorial. Vietnam is up here. This is the World War II Memorial. Now, the World War II Memorial, for those of you who haven't been, it's, first off, new, but it's made out of marble, and it's particularly thoriated marble. And that's important, because certain types of marble concentrate natural radiation emitters more than others, okay? And it just so happens that the marble they choose for the World War II Memorial is one of those. So we see here elevated radiation counts. Now, if I am using the quote-unquote dumb physicist approach, I say, aha, I have exceeded my threshold here. Set off an alarm, call in the Marines, whatever you're going to do. Obviously, we don't want to trigger off of the World War II Memorial. But here's the great news about it, is it's not going anywhere, okay? So I've got this information now. I've got some data that says, I know this spot here, known as the World War II Memorial, is radioactive. I don't care about that. Now, I care if somebody introduces a new source into this, but now I can start looking at data that's collected over a period of time and start informing future measurements based on the past measurements. And while this might seem like an obvious concept, radiation sensor networks, people were really starting to publish about them circa 2005. Circa 2005, they were stationary detectors. They maybe had about 10 detectors, 10 or 20 detectors on the system, and that was it. They weren't processing things simultaneously. They weren't looking at the response over the entire network. This is all stuff we can do today, but in 2005, they didn't have the computing capabilities. The term data science had not yet been coined. So looking at things like this, we started asking ourselves, well, how can we take advantage of this data that's already out there and aggregate it in ways that inform future alarms? Can I start improving that probability of detection and minimizing the probability of false alarms just by knowing what my distribution is here as historically measured? Another thing I saw as I was really starting to get interested in this stuff is this app here. This is called Gamma Pics. There's several. Okay, I'm just going to keep hitting that apparently. There's several apps like this out there, and what they do is they work off your smartphone. You can go download this today off of the iTunes Store or Google Play, and it takes the camera in your cell phone and it turns it into a radiation detector, no hardware modification required. Now, those of us who do detector physics, that makes perfect sense to us. It's a silicon chip, your CCD camera. Silicon is a great radiation detector. So this was obvious to radiation detection people, but now let's take a second and think, what if every single smartphone in San Francisco was a radiation detector? What would you do with that? That's a lot of data. What would you do with that? And moreover, it's not just every smartphone. We're talking every digital camera. So now I'm talking traffic cameras, surveillance cameras, ATM cameras, every digital camera, the body-worn cameras by police officers. They all could be radiation detectors. How do you make sense of that? You are going to have hits on that network. You will have false alarms. You will have what we call nuisance alarms. Nuisance alarms are true alarms. It's a truly radioactive thing that's setting it off, but maybe it's not a thing we care about. For instance, a patient, a medical patient who's gone in and had some sort of scan. Maybe they've had a PET scan for cancer diagnosis, or maybe they've had some sort of internal imaging study done. Those people are radioactive. They are truly radioactive. They will set off a network like this, but we do not care about that. That's not my nuclear weapon that I'm looking for. So when you're starting to talk about every single digital camera in a city, you have to think about how do we adjudicate alarms on this thing. That's a really complicated process. So DARPA comes out and says, okay, we're going to have this thing called Sigma. And we're going to take these detectors right here. This is a commercially available detector. It will detect gamma rays and neutrons. And we're going to put these in the hands of whomever, 1,000 of these detectors to make up one network. What they do is they communicate via Bluetooth to an Android smartphone. And so the radiation measurements are done here. The smartphone provides the time tag and the geotag. And then you upload that someplace. Okay, in our case, we're going to show you that we upload it into the cloud. You could do it into a server if you want. Maybe not the best idea if you're talking 2 terabytes a day, but we also have to think about how to adjudicate alarms on this type of system. So when I got involved in Sigma, which I got involved with them at the very beginning, and people were saying, 200 gigabytes a day, 2 terabytes a day, and those of us who were sitting in the back of the room, our heads started spinning and saying, oh my gosh, what are we going to do with all of this data? If you just use that the dumb physicist approach of 3 sigma, you have a 0.3% probability of a false alarm, just purely from Poissonian statistics. 0.3% times 10,000 detectors whose data is being collected once per second, and that's a lot of things that have to be adjudicated. So anything that can be done to make that 0.3% number less is a good thing. Okay, so tell you a little bit about what we're doing at Illinois. So we got involved with DARPA. DARPA was gracious enough to donate us a handful of about 23 of these detectors. And we got under contract. I'm pleased to announce that my research group opened up the entire state of Illinois to Amazon for Amazon Web Services. We could do this on Google. We can be cloud agnostic here, but we are not computer scientists. So we went with Amazon because of all of their pre-existing tools to help the non-computer scientists of us make cool things. So Amazon has been very helpful with us, and I do want to acknowledge that. What they have helped us do is we have our detector here, which is, like I said, paired up with an Android smartphone. And using their Kinesis fire hose and their Lambda functions, we take that data and every second we upload the data into an S3 bucket. And that's just our raw data. We're exporting CSV files. There's nothing that's efficient about this. There's all kinds of ways we can make it efficient, but right now, this is just our version 1.0 of our system. So we get this S3 bucket going. Every detector that we have dumps its data into this S3 bucket. And then we have another Lambda function that says, okay, when something gets dumped in here, now we're going to process it into some sort of form that we can use further downstream. Right now, what we're doing is we're outputting to a Postgres database that's hosted on an EC2 instance, which is fine for a small network, but it is not any sort of a distributed option. So our next generation, we are also outputting to an Amazon Redshift database, which is also Postgres, but now we're talking a more distributed solution where we can be doing some proper data science on that data set. And so last semester, by last semester I mean the spring semester of 2016, we took these 23 detectors, and I had an army of undergraduate volunteers, and their job was to carry these detectors everywhere they went, 24/7, and keep them charged. So that data set began in January. The semester ended in May. We're talking roughly 37 million, greater than 37 million points, over 150 gigabytes worth of data that's hosted right now on S3. Okay, so that's the data set that you're going to be seeing the results for the rest of the talk coming off of. Okay, so machine learning. Let's start getting into some of the real meat here. And the question that I asked earlier was, do we want to take the gamma ray spectra and try to make sense out of them, or do we want to take the gamma count rates and make sense out of them? We're not even going down the neutron path yet. We're not ready. But just looking at the data for gamma ray counts or gamma ray spectra, again, this data is collected once per second. So every second, I have a row in my database that gives time, GPS, the detector ID, the gamma counts, gamma dose, and then a 4,096 channel spectrum, once per second. Okay, so let's start by briefly talking about background. If you don't know background, you don't know diddly, is what this comes down to. Background is the thing that is always present that we have to somehow alarm in the presence of. When we talk signal to noise, that background is pretty much our biggest source of noise that we're going to be dealing with here. When we talk in the detector physics community, and we talk about something like 3 sigma, the quote-unquote dumb physicist approach, I have already made an assumption when I say 3 sigma, and that is that my data is somehow distributed in a Poissonian or a Gaussian fashion. Okay. When a first responder gets these detectors, they're not going out and doing some sort of calibrated setup to say, yes, I understand the statistics of my detector. No, they're putting it in their pocket and they're going on. So the data that gets collected in the field, we don't know, are they truly in the presence of a radioactive source or not? Are they doing whatever their path is in the World War II memorial, or are they doing it someplace with a much lower background? We don't know. But by assuming that we have a Gaussian distribution, we've already made a mistake. Okay, so this is looking at, this is 4 days worth of measurements of us just trying to say, what is the average background measurement for those 4 days? And what you can see is that we obviously, we've got a mean and some sort of standard deviation assumed, but we've got a whole ton of outliers. We can't control where these students go. Okay, there are some spots on campus, and you'll see them when we do the geospatial stuff, that are particularly radioactive. We don't tell them don't go there. They have to go live their lives, just like the first responders have to go and do their jobs. So if you were to actually plot, this is some subsets of some other data, but a few tests within that whole data set, you can see here, we've plotted this as a histogram, and I can measure the skew and kurtosis of that histogram. Now, for a perfect Gaussian, we expect a skew of 0 and a kurtosis of 3. I have nothing of the sort. Okay? So automatically, by just stating that we want to use the 3 sigma approach, we've made our first mistake. We can't do it just off of this data set. So in order for us to adequately say what background is, we have to start playing some fancy math games on this distribution. And what we do in my group is we use a trimmed and Windsorized mean, which helps us ignore some of these outliers. These outliers are only on one side of the distribution, by the way. Okay, those regions of higher counts. You're never going to have negative counts. Okay, so we trim and Windsorize this distribution to get a more accurate mean. To compare all of our measurements to. Now, radiation, I said, comes from material, comes from the dirt. It's not constant in position, nor is it constant in time, and this is what I mean by not constant in time. We can have a weather event such as precipitation, and what happens is it rains, the water gets into the soil, and that water forces out radon gas. Okay, that radon gas gets into the air, my background rate goes up. Okay? Never, ever have that radon count in your house done right after a rainfall. Okay, this is why. So we have to somehow take into account weather. And we tried to do an attempt where we took our entire data set and said, okay, let's just look at, was it raining that day or was it not raining that day? And what did our data look like? And in fact, we weren't able to separate out rain versus not rain. We have these two distributions here that look reasonably similar. Here's the problem. There's multiple things going on here. We don't know when the detectors were inside. When you are inside, you're not exposed to the dirt that's leaching this radon gas out. You have some shielding that's blocking cosmic radiation from you. There's all kinds of things at work here that we have to consider. So just looking at the entire data set, believe it or not, is not sufficient for us to tell the impact of rain. So we had to do a more controlled experiment whereby my postdoc, he decided that every day at lunchtime he was going to walk the same path around campus at roughly the same speed. Okay, now we knew he was outside. We knew what the weather was. We knew he was moving at roughly the same speed. And now you actually can see a correlation between your gamma background and rainfall. Ultimately, where we've been getting our weather data from is Weather Underground, which is a wonderful site for data scraping, and it's a horrible site for actually trying to learn anything about the weather. So we've gotten our own weather station up and running now so that we can have a more discretized measure of rainfall, wind direction, humidity, things like this. It's more than just rainfall. You have to look at how easy is it for the radon to get into the air, which is a function of the air pressure. How quickly does it get moved out of there? That's wind, right? So it's more than just rain, but you can clearly see that there is a correlation between rain and our measured gamma background. Okay, so now let's actually do some machine learning. The first thing we did, because I am a spectroscopist at heart, I said, let's start with the spectrum, because the gamma ray spectrum gives us a unique fingerprint as to what the isotope or isotopes that were present are. So I said, well, this is clearly the way to go, because this is what will tell us it's a nuclear weapon versus a medical patient. Let's start there. Turned out, wrong answer. I'm not going to pull the wool over your eyes. I'm going to tell you this is the wrong answer. Why? Okay. Principal component analysis. Okay, we're going to try and take our data set and represent it in a lower dimensional space. So for example here, if I have some sort of two-dimensional data set like this, you can see that it could be represented if we did a proper transform of axes. I have one component this way, and I have a little component this way, and I can rotate it about those two components and start representing my data in a little more of a clean way. And we said, aha, let's try doing that with gamma ray spectra. Sounds great. And in fact, there are people who do isotope identification algorithms based on principal component analysis. Fortunate for them, their problem is a little easier than ours. Okay, here's an example of 30-second spectra. So we had one detector, and we collected spectra for two different sources. This is cesium-137, cobalt-60 down here. These are some common lab check sources for the non-nuclear engineers in the room. And these peaks here, this one right here for cesium, and these two right here, those are the unique fingerprint that I'm talking about. The rest of this stuff is noise. It's background, it's Compton scatter, that's the physics of radiation interactions in material. We don't care about those parts. We care, is there something that is deviating from that shape, such as the presence of a peak here. And so what we did was we used principal component analysis to try and come up with a very quick way of getting this shape and saying, is there anything outside of that shape? And when you do this for 30-second spectra, yeah, you can do it. It works. Unfortunately, we do not have 30-second spectra. We have several 1-second spectra. We have a tested and training set here, as any good statistician should have. And here's what we found, was that our area under the curve, we could measure that. This is another way of looking at a Roc curve. The Roc curve is the probability of detection versus the probability of false alarm. Area under the curve is basically what percent is in the region it should be, i.e. if I had 0 probability of false alarm and 100% probability of detection, that would be an area under the curve of 1. Okay, these are normalized things here. And what we see is that as we start increasing the number of components of our data that we keep, we see that we can, within the first few components, represent most of our data. But if you actually plotted this as a Roc curve, K sigma is still performing better because we're talking about 1-second spectra. 1-second spectra, it turns out, look pretty bad. I'm going to skip through some of this. We tried this with a few different algorithms on 1-second spectra. Ultimately, what this boiled down to was that, yeah, PCA can work when you have 30-second spectra, when you have a probability of being able to have a peak in your spectrum. But in 1 second, the efficiencies of these detectors are not sufficient to be able to distinguish a peak from that Compton shape there. So we said, okay, everybody out of the pool, let's stop on the spectral route. Let's go back to just looking at count rates, which is probably where we should have started all along. So I have another graduate student, and he likes medical imaging. And he said, you know, this really is a medical imaging problem. We could do something like maximum likelihood estimation methods to try and get at when have we deviated from a Poissonian in some fashion. And so here's what we do. We know that we have background. We know that my background has a function of it of position, and it is a function of it of time. We know those are Poissonian distributed when we don't have the presence of a source. So we're going to assume a Poissonian variable here, lambda, that is going to be the linear combination of these two spatial and temporal components. Okay? And then I can represent the probability here of my measurement. D of x, y, and t is my measurement. So the probability of that measurement we are going to maximize as a function of this Poissonian variable, which is separated into these two, the temporal and the spatial components. Okay? So then we do a log likelihood maximization. We get some nice results. Let me just zoom in on what they are. This is taking our entire data set, the greater than 37 million points, and trying to eliminate the temporal variation and bring it back to just the spatial variation. So we've done the 37 million points and created a map now of our spatial distribution. And, okay, what we can see here, there's a few effects going on, and we're still working on this data. We have some regions of elevated counts. You see that there's a nice red region over here. Anybody can make a heat map, and anybody can make a heat map look like anything. But I'm going to show you where we can fool ourselves in a heat map. Okay, this is campus. So when we have data points here, I assume that our campus is very similar to your campus, which is that parking is a pain. And so my students who are walking these detectors are literally walking with these detectors. They're in their backpack or something. Now, if I get off campus where parking is a little easier, I'm in a car. Now, what happens when I'm in a car? First, I have the material of the car around me, and it's shielding my background measurement. Second, when I'm in a car, I'm moving faster. Okay, so if I happen to come across any source, like, you know, I don't know, let's say there was a source right at this intersection, I'm not sampling it for anywhere near as long as I would even in a 1 second thing. In 1 second, I've driven past it very quickly. I've not had the same number of photons hit my detector as I would have had I walked that in 1 second. Okay, so we have to be very careful when we start making maps like these because we can get into trouble very quickly. Okay. Ultimately, though, this boils down to the Roc Curve. Did we somehow do better than the 3 sigma approach by using this maximum likelihood method? And the answer is yes, we did. You'll notice that this is on a logarithmic scale down here. The K sigma, the quote-unquote dumb physicist approach, is the solid line down here. And you can see that that went up. That's what we want to see it do. We want to see at the small false positive rate, we want to see that we are having a higher true positive rate. So good, we've achieved some goodness with this. Now we have a lot of work to do with this. Okay, we want to go back and regenerate those maps as a function of velocity. Obviously, you know, we can't have my guy on foot get a completely different answer than my guy driving a car. That's bad. So that's some of our future work there. Okay, let's start talking some geospatial stuff. Okay, so obviously we have geotagged data. And I have, in many talks, said that geoint, meaning geointelligence, is the one truly unifying int. It is the one thing where any sensor network, whether it's radiation, chembio, explosives, anything like this, we care about where is the thing and when is it there. Any other form of intelligence, where is this bad guy? We want to find this bad guy. So geospatial intelligence is the one thing that truly can bring together a lot of scientists in this field. So I would encourage, particularly those of you who are students, you may think of I've got a GPS coordinate. Great, I plop that as a pin on the map, and I'm here to tell you that there is so much statistics involved in this. So we're going to talk today about things like data depth, and we're going to talk about robust statistics, and we're going to talk about all these different coefficients that we can use to quantify how spatially related are two data points. Okay, there's a lot to this. Do yourself a favor and take a course in GIS. It's truly fascinating stuff, and I can't do it justice. So if you ask me really hard questions, I'm going to give you the email from my postdoc at the Cyber GIS Center who's actually done this work. No, go back. Sorry, Prezi error. Okay, spatial clustering methods. Now, the idea here is that I have two data points. I know their physical separation, their Euclidean distance, but the question is, are these two measurements spatially correlated? So for instance, a lot of work has been done in spatial correlation in epidemiology. Zika virus, okay? We see that all of a sudden there are particular regions in Miami that all of a sudden we start seeing elevated reporting incidents of Zika. Is that truly statistically significant, and is it spatially significant? Can we say this is truly just Miami, or is this all of Florida? So we do all kinds of interesting math to try and say, do I have spatial correlation between my data? And when we talk about these correlations, we can talk about a global value and a local value. The global value will kind of think of it kind of like an average over my entire data set. Useful, but the thing that I really care about is the local value. Global values, here's a common metric of it called the Moran's I. Okay, these are just, you can go read about these in any number of geospatial books. We have this other method that we've been looking at called Geddes-Ord statistics. Another method, dbScan. These are just all some common algorithms within the geospatial community. But we need to talk about robust statistics first. I showed you the plot before showing skew and kurtosis of what we thought was a Gaussian that actually isn't. And it turns out it's going to really burn us here too. And the reason it burns us is because I am going to try and figure out a spatial correlation between my gamma ray measurements. We call this spatially lagged gamma ray counts. This is just a measure of that spatial correlation. I want to know, is there any sort of linear relationship between these two things? And here's my data. Okay, I have a whole bunch of data down here, and I'm going to try and fit it. Right. Okay, if I just do a least squares fit, I have all of this data out here. Some of these are outliers. Some of these are true measurements. We don't know which is which. I'm going to do least squares fit, and I'm going to come up with this slope. And by the way, that slope is my Moran's I. Okay, but we do know that at least some of these guys are outliers. So by applying that trimmed and Windsorized mean, what it allows us to do is to be able to flag the ones that are truly outliers and have a much better fit to our spatial correlation. This is important because everything that we're going to do is going to be based on, is there some sort of spatial correlation here? If we don't get this number right, we don't get the rest of it right. So we got to get this number right. Again, Windsorized trim means do not assume a Gaussian. We have no control over where these detectors go. Okay, so that being said, here's LISA. LISA stands for Local Indicators of Spatial Association, and what it's looking at, it's one mathematical way of saying on a region-by-region basis, I have high counts here, do I have high counts here? Now, what would I expect? The sources that I'm looking for are point sources, okay? We're talking about, if we're talking about a nuclear weapon, you guys, call it that big. I don't know, maybe it's got a maximum dimension of a meter. A few meters away from that, that acts like a point source. Here's where physics is not kind to the nuclear engineers in the room. Radiation follows a 1/r² pattern, meaning if I double my distance from a source, my intensity will decrease by a factor of 4. Okay, physics is not kind to us. But what that means is, because we know that, we know what the spatial autocorrelation should look like. We know that there should be this 1/r² relationship. And we can start applying this by weighting different geographic regions relative to each other. So if my source is this tree over here, I know that as I get closer to it and closer to it and closer to it, my count rate should go up. My count rate is a function of position here. And I care about point sources and not distributed sources. Distributed sources are like the World War II memorial. Okay, that's a big thing. The stuff that somebody who's up to no good is going to bring in is not a big thing. It's a point source. So we want to be able to get rid of the distributed things and find the point things. Make sense? So this is what we've done with LISA. And what you'll see, we have a LISA heat map up here. And you'll see that I have a region up here that is particularly, this is a particularly hot region on that heat map. And that is true. It's probably hard to see back there, but there's a building up here which is called the Nuclear Radiation Laboratory, NRL. It has a 12,000 Curie cobalt-60 source in it. And cobalt-60 is actually pretty radioactive, so that actually is a point source. So we would expect in a LISA analysis to see a great deal of heat in the region of a point source, which we do. Here, you see we've got like this one cell in particular that's particularly hot. There's a particular church on campus. It's got this very nice veranda that's made of thoriated marble. Again, I don't care about that, right? This is a distributed source. All right, so when we run this through LISA, we set a cutoff on our p-value. What's the probability that we truly have a point source? And in doing so, I go from this map up here to these cells. These are the only cells up here that were identified as having a p-value of less than 0.05. So it's clear that this is here, but if I squint my eyes funny over here, I don't see anything. I don't know what that is. For those who are the graduates of the University of Illinois, that's the Alma Mater. The base, we have a famous statue on campus, and it's standing on a base of marble. And when we're talking about scales, this is about 50 meters on a side, one of these cells. Alma is probably more like 5 meters on a side. So in this geospatial increment, that is a point source. So we actually are detecting the radioactivity of Alma because in that paradigm, it looks like a point source. So that's good. Okay, another one, robust G-statistics. This is another mathematical way that we can start looking at things. I'm not going to spend too much time looking at this data because this isn't the part that we care about. Robust DB scan, this is a method of looking at the clustering of data. What we really care about is the Roc curve, so let's get there. Here's the Roc curve for all these different geospatial methods. Now, the quote-unquote dumb physicist approach is this red line. This is back in linear scale. I apologize for the varying scales. So anything that we can do that is above this red line is good. Now, here's where we truly see the value of those robust statistics, of using those trimmed and Windsorized means. Here is G-statistics without having the robust measure. We're just using an assumption of a Gaussian. And you can see we actually do significantly worse than K-sigma. However, the second I apply robust statistics, now I go to the blue line. You can see just by using the a proper measure of the gamma ray background, we have improved our statistics that much. That is a win. Clustering, that's actually the thing, the black line here, this robust DB scan. DB scan is actually used a lot in sentiment analysis and like Twitter analysis. Text processing. But we used it in geospatial because ones and zeros are ones and zeros, and it actually has outperformed all of them. So I hope that by looking at this, you can be motivated to the fact that, did we do better than the quote-unquote dumb physicist approach? Yes. Almost everything, not everything, but almost everything that we have tried has been better than the 3 sigma approach. So hopefully that's something that makes my sponsor happy. Okay, last bit I want to talk about is sensor fusion. This is, you know, we've got all these detectors. We've been thinking about them as individual things. They're not individual things. The question is, if I have one detector up the hill over there and I've got another detector over here, why should I treat them as separate? They're part of a whole network. So we have to think about how do we start taking advantage of looking at all of that data simultaneously, looking at it back in time. How do we start bringing all of the network's data into play here? So there's a few things that any fusion problem has to do. The first thing is you need to align yourself spatially. Okay, that's pretty straightforward, you'd like to think, for using geocoordinates. Unfortunately, I am here to tell you that your smartphone does not have as good a GPS as you think it might. Those of you who play Pokemon, you know what I'm talking about. Okay, so we have measured our geoposition varying by up to 150 meters, 1 second to the next. Okay, that's bad, because all of my math is based on knowing the geocoordinates. So if I have a 150-meter error bar, that's bad. We have to align our data temporally. That's easier. We have timestamps. We know what time it is. We're pretty good with time. So we're just not even going to pay attention to time right now. We also need to talk about aligning the sensor measurements from different sensors. Those of you who are not radiation detection folks, if I have two detectors, exact same model, like I have two Ford Focuses, okay, they still perform differently. There's slight manufacturing variations. Maybe one detector is slightly more dense than the other. Maybe one is cut a little thinner than the other. These all matter. So every detector will have a slightly different efficiency to it, and that can create problems for us. So we need to think about how we align the detector-to-detector measurements as well. Okay, how could we do this? Well, Kriging is a very common way that this is done with other networks. And in Kriging, our whole goal is if we know something about our mean, okay, and our mean is a function, again, of position and time. I apologize, I represented it as mu here and lambda in a previous one. But I have a mean, and I've got an individual measurement, and it differs from the mean somehow. What we try to do in Kriging is to fit this such that we get these weights here. And my weights are somehow going to, maximize my probability of a particular measurement having happened. A few different ways this can be done. First off, there's simple Kriging, where we know what that mu value is, and we know it's constant. Okay? Not our case. We don't know what our mu is. We know what it has been in the past. We have a rough idea through machine learning what it might be today, but right now we're going to assume we do not know what that mean background value is. Further, we could go into ordinary Kriging, where we say we don't know what it is, but we assume it to be constant. Also, bad assumption in our case, because we've seen how things like rain can impact our mean background measurement. So instead of using simple or ordinary Kriging, we are forced to go into universal Kriging, which is quite a bit more mathematically intensive, but we're going to start talking about expectation values here. And in universal Kriging, we assume that there is a linear function that represents my measurement, my measured value at every point. We have an expectation function here. Lots of math goes into this, but let me give you what the punchline is. The punchline is that if I compare the expectation values of two different measurements that may have two different background values, if you work the math out, what you wind up with is that it's just the covariance. The expectation value is just the covariance between the two different measured points. Now, what do I mean by that covariance? Is my error in my measurement here at all influencing my error in my measurement here? Gut response should tell you no, there is no covariance. But we actually measured it using our entire data set, and we found that our covariance was down on the order of 10 to the minus 5. So I'm good enough with calling that 0 to say that universal Kriging works for us. So when we say that, now what we can do is we can start making maps. And this is just one quick map of like one track's worth of data. But we start making maps where we create that alignment around our mean value that is neither known nor is it constant. And what this does for us is this starts telling us the World War II memorial is always radioactive. We can create maps of whole regions this way. Now, it is computationally intensive. My group, like I said, we are not computer scientists, but what we have been doing is we've been doing things like using Spark and Spark SQL to do this math, to start saying, here's what this map ought to look like. This is very much work in progress for us. Stay tuned. A year from now, we'll have the entire planet completely krigged. I'm kidding. Okay, so let's talk about future work now. Where are we going with this? Obviously, we have a lot of work to do on this Kriging, but it bears the probability of high payoff here. Having the ability to say to a first responder, yeah, you know what? That World War II, that memorial you're standing in right now, yeah, that's got a higher probability of having higher gamma background. So, you know, we're going to set our alarms differently based on geopositional information. Okay, so that we believe will have a huge payoff on our Roc Curve. Fusion of other data types. I've only talked to you really about gamma counts. I steered us away from gamma ray spectra. I haven't even said anything about neutron counts. And Lord knows I haven't brought anything in really hard like LiDAR or other imaging modalities. We haven't brought in the velocity of the detector. There's all kinds of other things that need to be brought into in our overall data stream. Weather. We're collecting this weather data. We're in the midst of fusing it right now. It's its own little SQL merge fun. Proxy signatures of proliferation. All this is well and good. We've got these measured data points, but I don't have ground truth. Anything that I can do is semi-supervised at best. Okay? Fortunately, I don't have cases that I can point to saying, this is what happens when somebody tries to smuggle a nuclear weapon into a city. Okay, knock on wood, I never have that. But we do need to develop math around this. So we are always looking for different proxies for that same problem. I'll give you an example. Non-proliferation, or proliferation, obviously very strongly in the news today. And the question is, what data sets are out there that might look like that, that aren't truly examples of proliferation, but have known answers that we can use supervised learning on? And one example that was suggested was earthquake detection on Twitter, which I would think would be something of interest in the Bay region. Can I, using only Twitter, no other source of information, an earthquake happens, can I determine its magnitude and its epicenter using only Twitter? Okay, well that's kind of fun. I start looking at tweets. Some people choose to give their geo-coordinates, some people don't. They say, aha, I just felt that, felt like a truck driving by. Okay, well, that's going to be one magnitude. Another tweet, and we certainly saw this in the Haitian earthquake, my house is on top of me, somebody come help dig me out. That's a different magnitude, right? So we can look at things like sentiment analysis. We can do clustering on the tweets themselves. That DB scan method was developed for doing just that. So that type of proxy is what we're always looking for, other proxy problems that might look like proliferation. And then obviously, you probably don't have a single person come into this room and give a talk that says, oh, I have enough data and it scales fine. Okay. Obviously, we need to be looking at how does our process scale up? How do we ingest more data? How do we do it in real time? Because it doesn't do any good for me to have my calculation take 1 year if somebody's brought, if there's already a big stinking crater in the ground. So what my group is doing is, as nuclear engineers, we're trying to do enough data science to improve that Roc curve, increase our probability of detection, decrease our false alarm rate, and bring in people from other disciplines like geostatistics, GIS, to help in that effort. So that is my last slide. I want to thank you guys for coming and putting up with a really boring talk right after lunch, and I'm happy to take any questions.